Hello and welcome. In this video, we're going to look at how to calculate the series RLC current in this circuit here. So to get our total current, we need to apply Ohm's law. So we'll pull Ohm's law back out, our voltage, current, and resistance. If we're looking for current, we need voltage over resistance. And since we have an RLC circuit, we actually need to get our total Z value for the whole circuit and then use that into our Ohm's law. And so that is where we're going to start off with in finding our rectangular form of Z, which means that our Z is equal to our resistor plus or minus J X total. We'll find that first, which means that we need to figure out what our XL and XC values are so that we can get to X total, because X total is the combination of our XL minus our XC. And so we need to find XL and XC. So XL is equal to, and XC is equal to. XL is that 2 pi FL equation, and XC is that 1 over 2 pi FC equation. And so we'll plug both of those in here. 2 pi, go for our XL first, 2 pi times our frequency of 21,000 multiplied by our inductor value. Watch out for those millihenries. You can do 1.3 times 10 to the negative 3, or you can move that decimal point, 0.0013. So our XL is equal to 171.7. 0.5 if we needed to, but we don't, so we can just put that as an ohmic value. We'll do the next one, our XC. Send out, we'll go 1 over 2 pi times 21,000 times our capacitor value. Capacitors are usually pretty small, that nanofarad, so I don't want to put all those zeros in. So I'm going to put in our full notation, 13 times 10 to the, and nano is 9, so negative 9. So that gives us an XC value of 582. We can round that up to 83. So back up on there, 83 ohms. And so now our X total can be calculated out. We now know that the capacitor 1, right, because XC is larger than XL, so the capacitor 1, which means that your J value way down here, that positive or negative, is going to be negative because the capacitor 1. Right, and that's kind of indicative of this equation here. XL is in front of XC. So we'll type our XL first, 171, and subtract our XC, 583, which gives us a negative number, meaning that the capacitor is bigger than the inductor as far as what it's doing to the circuit. Negative 412. And so now we can plug that in for what we know our Z value is, because we know what our resistor is. It's 240. We know that our capacitor 1, so it'll be a negative J. And then our X total was 412. That is our first Z answer here. Plug that in. So 240 negative 412. Put that into rectangular form for our next answer. So we'll take our square root equation. Say that we have 240 squared plus, technically this negative is there, right? So if we put in a parenthesis, we can say negative 412 and square that, and we end up with a positive anyway. So regardless of this negative here, it's a negative times a negative makes it a positive, and we end up with a positive answer as our output. So this is our first magnitude for our polar form of Z. So Z is also equal to 477, we'll round that up, at an angle of, we'll figure out our angle using our tangent equation, inverse tangent of our second number, which is negative, so negative 412 divided by 240, our first number, gives us a negative 59, so negative 60. Round that up. And that is in ohms here. We'll plug that in as our second answer, 477, negative 60. Again, that negative here is because that capacitor was bigger in our X total equation. Right? And so that's where that all comes from. So keep an eye on where your negatives are coming from. Last, we get to apply our Ohm's law. So now we knew that our Ohm's law over here said current equals voltage over resistance. We now found our total resistance for the circuit. Now we can divide them. We were given that our voltage is 15 at an angle of 0. So we'll say 15 at an angle of 0 degrees. This angle does matter here. Divided by 477 at an angle of negative 60 degrees ohms. Right? Voltage divided by resistance gives us current. And so we're going to evaluate the first two digits, 15 and 477 together, and then we'll deal with the angles afterwards. And so we'll just divide out these two here. So 15 divided by 477, start there, 15,477, gives us a really small current. We want it in milliamps, so we'll move that into milliamps. We'll say 31.44, so 31.4 at an angle of, use our tangent equation. Or no, we'll subtract them. Okay, so in this case, we want to take our top number, and since we divided the magnitudes of these 15 and the 477, we want to take the number that's with the 15 and subtract it from the number that's with the 477. And in this case, we have 0 degrees with our 15 number minus, open parenthesis, negative 60. Right? This first negative says I divided the magnitudes. The second negative says this angle that I divided the magnitudes of is also negative. We have to account for both of those because they will cancel each other out, which means that this one and this one, negative negative, becomes a positive, and our answer becomes positive 60 degrees. So 60 degrees. We'll plug that in for our final answer here. And it's in milliamps already because we moved that. So 31.4 milliamps at positive 60 degrees. We'll check that. All right. So if you guys have any questions, feel free to reach out.